All right, what about now?
Okay.
All right. I will be talking about beam diagnostics or instrumentation. Yeah, so first of all, good morning, everybody. All right, so what is the beam diagnostics? So let's assume that we constructed this fantastic accelerator. How do we know if it even works? Right, the beams which are in the machine, you may think because of radiation protection and all these measures that they are very strong, but actually, at least at the beginning, where you actually start running your machine, the beams are usually very low intensity, and they are not easy to be seen. Nevertheless, you have to see them, and therefore you have to have a means to measure measure them. And it's not only at the beginning; it's also during the operation. It's not only that you have to check if everything is fine all the time, basically continuously. There are beam instruments that are working continuously, but also sometimes you have a problem and you have to debug your machine. You have to check what happened. Is the beam lost somewhere? And here again, you need to measure. More instruments you have, easier it is to debug the machine, to tune the machine. And this is, in general, the field of beam instrumentation, also sometimes called diagnostics. Manjit at the first lecture said that diagnostics of a patient is the art of seeing, and it's true, diagnostic is the art of seeing. In this case, it's not a patient, but the beam. And here in this presentation, I will just focus on the most important measurements because there are really a lot of techniques and a lot of different instruments that are possible. Here you see a typical control room. This is actually from LHC, but it doesn't matter. I think roughly half of the screens are screens related to beam instrumentation. Okay, the other half are vacuum, power converters, access system, radiation protection, but half, 50% is various beam instruments. So it is really a big, very important part of the operation. And on the next slide, yeah, the question is what to measure. You have these plots with various, let's say, images that are seen in the control room by the operators from various laboratories. So of course, what you measure the beam properties, the beam current, the beam position, the beam emittance, and then beam losses. You do also measure beam energy. However, usually this is very well defined by, let's say, yeah, but in the synchrotron, it's well defined by the machine state. In cyclotron, it's fixed. You measure the momentum spread, and in the synchrotron, you usually measure the tune, chromaticity, sometimes online, sometimes periodically, longitudinal profile of the beam, and there are a lot of other little measurements that are done, like beam halo, spill structure, divergence of the beam, optics errors. Part of these measurements are on the border between the instrumentation and, let's say, actually beam dynamics. Okay, so there are not only instrumentation people participating in them, but also people who calculate the properties of the machine. All right, so let's start with what is a measurement? Well, we know from quantum mechanics that basically every measurement disturbs the measured object. And if you look, here is an example of, oh, it went the wrong way, sorry. An example of, it goes wrong way, of a Schrödinger cat. And the cat, as you know, is alive until the moment we measure it. Then when we measure it, okay, we don't know in which state it is before we measure. And when we measure, it's either dead, so the measurement affected the cat, or it's alive, but definitely the cat noticed that the box was open. So, okay, so there is no measurement which is completely not affecting the system. However, for us, of course, we are not a quantum, most of the time, we are not the quantum system. So small measurements are not destructive, don't really affect the beam. We don't see effect on the beam. But there are some measurements which are really invasive. And these invasive measurements, they destroy the beam completely. And you will see on the next two slides such examples of measurements. Sorry. There are the main phenomena which are used in beam measurements, the main physical phenomena. If you think about it, basically there are three main. There are then a lot of other phenomena which can be used, but in principle, the three main things which are used are electromagnetic induction, because a beam is a current that goes through your machine, and you can measure this current somehow. There are various ways. Then there is a secondary electron emission, and I will show you where it is important, and ionization of gases. These three phenomena basically cover probably 70–80% of all beam instruments. So let's start with beam current measurement. It's a current, so the best way to measure it is induction. And here you see something that you are probably familiar with. It's a current meter that everyone has at home, which uses electromagnetic induction to actually measure how much current went to your apartment and how much you have to pay for it afterwards. We have a similar device to measure the beam current in the accelerators. It's called beam current transformer. And basically what you see here, the red bar is the beam, and the beam generates magnetic field around it, yeah, like normal cable. And if you, around the beam, if you put if you install a torus, metallic torus, then you catch this magnetic field. And if you put windings around this torus, then actually it will generate a voltage. And you can measure this voltage, and this voltage is proportional to the current of the beam that goes through it. Yeah, well, this generation, as you probably know from Maxwell equation, can only happen if the beam is pulsed, right? So you cannot really measure DC beam this way, exactly this way. And here you see an example of what is sent through the torus. This is a test pulse. So this is not the real beam. Sometimes in order to test this beam current monitors, you just put a cable inside and you send pulses. You send the pulse, and then you reconstruct from the voltage here, okay? And here you see the reconstruction from the test pulse, and here is a real beam bunch, which is longitudinally very often Gaussian. So you have various things here. There is a drop time. So if your test pulse is very long, then actually it drops to 0, and you know, this is why you cannot measure a DC beam in this way. However, what is important is a non-destructive measurement. You can keep this device switch on all the time, and it doesn't really affect the beam, except of quantum effects, but as we said already, they are not important. There are basically three types of beam current transformers. There's a passive transformer, which is exactly the device I shown you before. It's quite fast, but it has rather poor sensitivity, around 10 microamps. Then there are active transformers, which basically work the same way, but have an active readout system where you actually amplify your signal and you can get much better sensitivity, but this amplification makes them a little bit slower. And then there is a direct current transformer. I will not go here in the details, but in principle, you can try to put two toruses, compensate the scene effect, and you could measure direct current. However, the sensitivity here is quite large, it's 100 microamps. So this is a not destructive, very popular way to measure beam current. Another way, which is present in most of the machines I'm aware of, is Faraday cup. Faraday cup works very simple way. There is it intercepts the whole beam, so the beam enters the cup. Yeah, it's why it's called a cup. Enters and is completely lost here on the cup material. Because the beam carries certain charge, then of course this charge is carried inside the material, and you can measure it through a simple charge meter, basically. Of course, you can do it only for low energy beams, because at high energies you start having problems. The beam can go through, or some components, particles which are producing the interaction of the beam with the material of the cup will leave, and the cup can be destroyed. So these Faraday cups may only sense up to energies of several mega electron volt per mass unit. It's completely destructive measurement, so you cannot just keep it running. but has very good sensitivity of the order of nanoamps. So here we have 100 microamps for DC beam, and here we have nanoamps for the same DC beam. Then the next very important thing is beam position measurement. Beam position measurement uses again the electromagnetic induction. And how it works? There are several ways of doing that, but this is the way which is used in machines like hadron therapy machines, where beams are not very fast and the bunches are actually very long. It's called the shoebox cavity. Well, it's because it's yeah, I don't know exactly where the name comes from, but yeah, somehow maybe somebody had a shoebox in this shape. Basically, you have a vacuum chamber which is square in the section, and you cut it diagonally. So you have kind of two electrodes, left and right, and they have this shape. And then when beam goes to this is the center of the machine, or the reference orbit, let's say. When beam goes to the right, then of course this electrode sees much higher voltage than this electrode. When you subtract the voltages, you can find the position of the beam with respect to the beam center. So this measurement is also not destructive, right? These devices, they are running all the time in synchrotrons, and they provide accuracy of around 0.1 millimeter. In some other machines like electron machines, slightly different methods are used, and they go to accuracy of the order of hundreds of nanometers or even tens of nanometers. And here you see a readout from a set 12, 1, 2, 3, 4, yeah, 12 of these BPMs, beam position monitors, in a machine like KNAU. And this defines your orbit. And here is an example of orbit measurement for different energies. You see that this is a very good thing here. The orbit is very reproducible in KNAU. And this is really what you want to have if you want to have reproducible irradiation at the patient afterwards. Okay, the next measurement is a tune measurement. If you remember, a tune is the number of oscillations, the betatron oscillations that particles do when they go around the synchrotron. And tune is measured in many ways, several ways at least. But the most common measurement actually uses the beam position monitor and the exciter. So you excite the beam transversely. You give it a kick. We say you give it a kick. And here you see this is a very fast kick. Beam is immediately excited. And it slowly decays because we are lucky. And in principle, these transverse excitations, they decay because of beam interacting with the machine. But it decays and it oscillates. You don't see these oscillations here, but basically you can imagine that the position of the beam oscillates. And when you do the Fourier transform of these oscillations, then you can measure the main frequency of the oscillations, and this main frequency is the tune. Okay, and here you see what is seen in the control room, and I don't remember where is it from. Maybe it is from GSI actually. The point is that here you don't need very fancy electronics for this very basic measurements. You just use a commercial spectrum analyzer. You connect it to your BPM, and maybe in your BPM you need a little bit better amplification of the signal, because usually your spectrum analyzer is in the control room, so it's quite far. But yeah, this is the measurement that is done. You actually would be surprised. I mean, if you go to very modern control room, then you see a lot of digital applications that measure various things. But actually, some years ago, accelerators were run using oscilloscopes and spectrum analyzers, and that also worked. All right, then we go to beam emittance. If you remember, we speak a lot about beam emittance. It's a volume in the transverse phase space which is occupied by the beam, and I think it's the third time that this plot is shown here. We have position of the particles and the angle, and we would like to measure this. Of course, it's difficult to measure position and the angle at the same time. You will see it is done, but not always. But if you know the beta function of your machine and you are in dispersion-free region, then in principle, by measuring the size of the beam, you already can get the emittance, right? If this is 0 and you know the beta, then you can get the emittance. All right. Now, how it is done when actually the angle is important and you're not sure what is your beta value, which often happens at the low energy part of acceleration, of accelerators. Well, you measure it using a grid profile monitor. So first of all, let's talk a moment about the secondary emission electrons, because this is a very important process. I think ionization, you probably everyone knows, but secondary emission is not so well known. What is the secondary emission? This is this upper plot here. When the particle hits a material, here it hits, but actually it enters the material, it excites electrons. Yeah, some of the electrons can get very strong excitation. The direct kick to the electrons is actually a lot of momentum transfer. These electrons reach energies of kiloelectronvolts, yeah, large energies. And sometimes they leave the material, but we are not interested in these electrons. There is something which is kind of excitation of all electrons in this very surface layer. And some of these excited electrons, they get enough energy to go out. This is so-called secondary excitation, because it's not this primary electron that is kicked by the beam particle. It's the excitation of the electrons because there is this primary electrons already in the material and because the material structure is excited. And these are called secondary electrons. They have just few electron-volt energy and they go out of the skin of the material. And the number of those electrons is quite small, but we have a lot of beam usually, and is proportional to the beam intensity. So if we measure these electrons, or if we measure the current which is carried away by these electrons, then we have idea about the beam current. And here you see an example of such a measurement. So you have a beam. In some point you put a slit, and out of the beam you choose only a very small part, very small part of the beam. We call it the beamlet, a small beam. Yeah? And this small part of the beam travels to a profile monitor, which is usually made of these grids. We call them SEM grids because they are the way of measuring is the secondary electron emission measurement. And we measure we measure on how many grids. Yeah, here is a profile monitor in general, but imagine that there are points here where the beam intensity is measured. So you measure the divergence of the beam for every position. So basically, you can imagine that you are looking at this slice, and you measure basically this Gaussian distribution in the angle. And this allows you to reconstruct the phase space of the beam at low energy. It's called the slit grid system, and measurement is of course destructive, but it's very important. It's one of the most important measurements that you do when you commission your ion source, for instance. All right, here you see some examples of such measurements, actually from CNAO and from GSI. And you see, for instance, that this nice image that we carry all the time with us, that the beam is Gaussian. It's not true. Most of the time is actually, for this low energy part, the beam is not Gaussian. It's very important to know the phase space. Okay, and at high energies, we can use various things. At high energies, we usually know the beta function, and we just measure the beam size, and from that we reconstruct the emittance. And there are many ways. Here is my favorite way because I spent quite a few years working on this kind of device, which is called ionization profile monitor. So it makes use of the third process, which is ionization process. You have, the vacuum is never perfect. You always have something which is with some rest gas. If it's not enough, you inject a little bit more. And when the beam goes through this rest gas, it ionizes the gas. Now, if you have electrodes which extract electrons or ions from this beam area, then and you register them with a position-sensitive device. Here, or in our case, here is just amplification, and you register with a camera outside of the vacuum. Then you can reconstruct a beam size. And here is exactly what you see. This is in GSI, and this is actually a kind of commissioning, and you see there are a lot of problems, reflections. But this is the beam, the measurement of the beam in the synchrotron using this kind of device. It's called ionization profile monitor. And here I conclude. So measurements allows to instrumentation allows to measure what is in the machine, and this feedback is really necessary to reach the design performance or even to start the machine. The main measured quantities are current, position, emittance, and tune. And the main physics processes used by these instruments are electromagnetic processes, electromagnetic coupling, secondary electron emission, and gas ionization. And there are two types of measurements, non-invasive and destructive. And non-invasive, typically they run all the time, and destructive, they run only in the periods where you commission your accelerator. Thank you very much.
Thank you very much, Mariusz, for that very interesting talk. Shall we see the questions?
In fact, there is no question posted in the document. So
shall we put up the link again, just in case somebody wants to ask questions?
Yes, and meantime, if people want to ask online, they can unmute themselves or raise hands or type in the chat. Actually, no questions.
I was so clear that everything is fine. Or
yes, you had many questions in the previous presentation, and now things
we have one question.
Okay, one question came.
Hello?
Yes, so and somebody wants to ask online a question.
Yes, let's start with the online question. Yes, we're hearing you.
Yuta?
Yes, yes, please. Yes, please. We hear you.
Please go ahead.
Okay, a student of mine wants to ask one question, please. Okay?
Please go ahead.
Hello, my name is Mariam, and I have a question about what is the relationship between electron emittance and the beam ion used to treatment.
What is the relationship between emittance, the beam emittance, and the electron?
And ions, beam ions used to treatment.
I'm not sure I understood. I mean, in principle, we don't have electrons there. I said maybe in ionization profile monitors, we use the electrons to measure the beam size, but yeah, they don't have particular emittance. They don't form a beam. It's just a way of measurement. I'm not sure if I understood.
Yes.
If you want to clarify, feel free to fill in the form so that it makes it easier for us to understand what the question really is.
Yeah, or contact me also.
Hello?
Yes?
I have another question. What does the beta represent?
What does the beta represent? Is that your question?
Yes.
The beta in the equation to measure the emittance, in the emittance equation, right?
Okay.
It's the optics. Yeah, I was not clear. Maybe it's the twist beta. So it's the optics of the line or of the machine. So this is something that it's also measured actually, but we have some theoretical values for that. Yeah, in principle, we know it, and from theory and from other measurements. And when we know it, we can reconstruct from the beam size, we can reconstruct the beam emittance.
So Mariusz, regarding the previous question, Stefan provided us with a clearer picture of what she meant. I think she meant what is the difference between emittance and the beam energy for the treatment, if I'm understanding well.
Oh, okay, yes, yeah, right. Well, the beam size which is needed for the treatment, of course, well, let's say if you have very big emittance and you want to have a small beam size on the patient, then you need very strong focusing. Sometimes it's even impossible. If it's too big, you cannot focus too much, right? So this is the relationship. So for instance, the emittances in hadron machine like CIST will be, or Heidelberg, the normalized emittances are around 1 millimeter millirad, and that allows, so you have this emittance, and then you can still focus to different beam sizes on the patient, somewhere between 2 and 10 millimeters. All right. Now, if your emittance would be 1 meter, it's completely crazy, but imagine 1 meter millirad, then basically you would need a huge quadrupole, like a big, like Eiffel Tower, to focus the beam on the patient to 2 millimeters. Is that image somehow working?
I think it's quite clear.
Maybe I go through the other questions, but please really contact me if something is not clear. Is it possible to measure proton beam shape using the camera? Yes, it's possible, depending where. So, for instance, at low energy beam part, so in LINAC, where beam goes only once through the structure, you could imagine to inject a gas. We call it a pressure bump. So locally increase the pressure of the gas of the rest gas in the machine, and when beam goes through this gas, it ionizes. Well, you have fluorescence basically. So the gas is ionized and emits light, and you can just have a window in your vacuum chamber and put a camera and see the beam. It's very easy. You cannot do the same in synchrotron because beam comes back all the time to the same place. And of course, every time it goes through the pressure bump, it's affected very strongly. So let's say in the LINAC where it goes once, it's fine, but in the synchrotron, you cannot use this beam-induced fluorescence monitors. We call it like that. How do you measure the beam sigma? Well, basically you have this profile. Let's say you register the beam image with a camera, like I said before, and every pixel carries information about the intensity of the light. And of course, when you make a profile, then you will get Gaussian, and you can just fit the Gaussian and get your sigma. Reliability of beam current measurement using a beam profile monitor signal. This is actually explanation. So maybe let's put it like that. I think what you mean is that beam. We didn't talk about this, but you can. That's what you do actually.
Of your camera?
Sorry?
Okay, we asked respondents to switch off their microphone, please. You can continue, Mariusz.
Thank you. You have the ionization chamber and beam goes through. It's again in the transfer lines where you know, beam doesn't come back because every time it goes through a material, of course, it's affected and it's not a good thing. But we can afford to do it once. And when it goes, so we have this flat ionization chamber. And the ionization chamber works in this way that basically the signal is proportional to the beam intensity, and it's very stable. So small changes in pressure and pressure maybe not, but at least in high voltage do not affect the measurement. Now, usually after the ionization chamber, we have multi-wire proportional chamber, which is also ionization detector, but it works a little bit different way. There is so-called gas gain in play. So you get much significantly larger signal than from ionization chamber, but you are much more sensitive to, let's say, variations of the high voltage, etc., etc. So sometimes people use just the multi-wire proportional chamber also to measure the beam current. Sometimes these measurements are decoupled because, you know, the two devices, they work in a different mode of operation. One is optimized from beam current measurement. The other one is optimized for beam position measurement. Do you know what size and emittance they have? There will be beams incised at fast mode. Yes, we do at fast mode. So with fast extraction, basically the emittance will be the extracted beam emittance, so 1 millimeter milliradian. And then the beam size, as I said, we modify by focusing the beam, right? Or as Elena explained before, if we have this bar of charge, we can also rotate the beam. There are two ways of controlling the beam size. What about a measure of the resonances and the beam stability? Yes, this is a very interesting point. I don't know if you remember in my lecture, I was showing at some point a graph from GSI machine where the resonances were measured. So usually how you measure it, you measure the lifetime of the beam. You inject the beam, you bring it to certain values of the tune, horizontal, vertical, and you measure how long the beam stays in your machine. So beam is lost. If you are in the resonance, the beam is lost relatively fast and your lifetime is short. And this allows you to measure the resonance, basically. Yeah. How much of the beam will be lost in an ion therapy session? Well, most of the beam, so let's say you have two main points where beam losses occur in a synchrotron. The first point is injection. The second point is extraction from the synchrotron. So basically, you lose roughly 50% of the beam in these two processes. But then after extraction, basically we transfer most of the beam, 99%, I would say, all the way to the patient. And the beam is lost on the patient. So the poor patient is the beam dump for a little moment, but this is what we want. And actually, because beam is lost on the patient, there are a lot of neutrons coming out of the patient, which have to be shielded. So nobody can stay next to the patient because, yeah, I mean, if a personnel stays regularly next to a patient, then it gets actually some significant dose. Doesn't the measurement by induction change the beam itself? Short answer is no. Longer answer is a little bit, but no, in principle, no, it does not. Let me get the definition of tune. Yeah, the tune is the transverse, the beam oscillates transversely in the machine. Yeah, you remember that there are quadrupoles, which are this have parabolic potentials, and the beam oscillates in these potentials. And the number of these oscillations is tune. We spoke about it several times. If tune is an integer, then machine is unstable in principle. However, sometimes we want it, and at half integer or third integer tune, actually the extraction works. My email, yes, I can give it. Maybe you can write it. I don't know who is writing. Aris, you just write my email here, and please contact me if you have problems or questions. I think we can put femtosecond camera on a lot of places to measure the beam. Is it right? Yes. No, I don't know. What do you mean by femtosecond camera? This is a little bit tricky question. I mean, you have this kind of, so first of all, we are not working in femtosecond scale with hadron machines. The bunch length is of the order of some hundreds of microseconds. So we are very far from this very advanced ways of beam measurement. What you are referring to are very specific measurements, which are usually done for let's say, electron machines, but not really for hadron machines. There are also some, but not in a hadron, not in the medical machines. Is the emittance of a cyclotron similar to synchrotron? This is a good question. So the extracted emittance is not, because cyclotron is basically a cyclotron which changes the frequency during the operation. So the extracted beam is still the nice ellipsoidal in both planes. While in synchrotron you have this bar of charge. However, in the machine, basic emittance is similar. Inside the machine, in synchrotron and in cyclotron, for medical applications, I think we have similar emittances. Can we use cyclotron for carbon ion acceleration? Yes, there is a project like that. It's a really huge machine, and most people think it's not a good idea. It's better to use cyclotrons. And the reason is that the machine is really large and you have a lot of losses. Don't forget, when you have a cyclotron, you have to reduce the beam energy after extraction. So you need to have a zone where a lot of beam where beam has to go through material which reduces its energy, degrades its properties. So altogether, we think in general that it's better to use synchrotrons. However, there is a project in France to build a cyclotron for carbon therapy. Any specific diagnostic changes for flash? Oh, this is a very, very interesting subject. Yes and no. So in principle, flash, we are still thinking how to do flash with synchrotrons. I think you've seen that the first day there was a statement that synchrotrons are not very good for flash. Cyclotrons, yes. Well, I think you can get flash with synchrotrons by just fast extraction. So this is what Rebecca was talking about yesterday, that the simplest way of extracting beam is just kick the whole beam in the extraction channel. And in this case, you can easily get flash conditions on the patients. Now, we do know very well how to measure the beam in this fast extraction mode. There is no problem with that. It's actually sometimes easier than slow extraction. However, of course, there is no way to stop the beam. The beam pulse is very short. So all these ways, like to stop the beam, when you say, okay, something is wrong with your machine, you should not send the beam to the patient. You stop the beam in the middle of irradiation, it will not work because you just send the whole beam in one go. Yeah. What is the definition of beam extraction? Basically, yeah, the beam extraction, that's a question to Elena who spoke before me, is you extract the beam, you have a circular machine where the beam is. Now you have to send it to the patient. Therefore, you have to extract it. This is the definition. I'm not sure if that answers the question.
Okay.
The point is, it's not so easy, not so obvious how to do it. Yeah.
Mariusz, thank you so much for your presentation, for answering all the questions. I have placed Mariusz's email address in the chat, so anyone who wants to elaborate further is invited to ask Mariusz questions via email. Furthermore, we are circulating a poll, which we urge you to answer. And in the meantime, I would like to introduce you to the next speaker. Mariusz, thank you very much for everything. I would like to introduce you to Matej, who will be giving us an overview and an introduction to the basics of accelerator control systems. Matej, you've got the floor.
Can we hear each other?
Yes, loud and clear.
Okay,